Alright, so I've been seeing a lot of correct answers. So yeah, the factorization. So the two numbers, first of all, negative 18, they sum to 7, they multiply negative 18, that would be minus 2 and positive 9. And so yeah, notice again, negative 2x plus 9x is 7x, negative 2 times 9 is negative 18. All right, and yeah. So some of you may have gotten the sign reversed. You might have gotten like x squared minus 7x minus 18 when you're trying something. If you see this, you can just literally reverse the signs of the two numbers here, and then it'll give you the right thing. So yeah, don't just. So yeah, if you accidentally get like the near term negated, you can just like negate the other terms in your tries to like not have to totally trash that attempt and go bash some more. And yeah, that's just factoring that's just the basic example of factoring quadratics. And now moving on to more. We can also look for perfect squares or perfect differences in some special like polynomials or quadratics that we factor. Remember that because the formula for jx plus k squared is j squared x squared plus 2jkx plus k squared, which you can just literally like write jx plus just k times jx plus k, and then term by term multiply it. This times this, k times jx, and then also k times jx here, and k times k. And when you add it all up, simplify it, expand, this is what you'll get. You can verify this by hand pretty easily. And since you know this, you can identify polynomials as perfect squares if b squared is equal to 4ac in the quadratic. In b squared, b, a, and c correspond to the a, b, and c in these terms. And yeah, we'll see more about like the relationship between b squared and 4ac later on. It's actually pretty important. So yeah, but just know that for now, in perfect square quadratics, b squared and 4ac are equal, assuming we're talking about standard form. Note that if b is equal to 0 and c is less than 0, we can factor it as difference of squares. So, b is equal to 0 means there's no linear term. So we treat ax squared and c as the square of x root a, as well as c being the square of just root c. So this gives x root a plus root c times x root a minus root c in general. There are nicer special cases like what x squared minus 1 is equal to x plus 1 times x minus 1. But yeah, that's just an example of difference of squares, what I mean by that. An example for a square root binomial, like let's just say you have x plus 1 squared, and that's just x squared plus 2x plus 1, right? You can just plug into this, or you can just directly expand x plus 1 times x plus 1. And yeah, oh wait, there's no 1 here, all right. And that being said, factor these two. The first one is a perfect square, and the second one is a difference of squares, just a little giveaway. I mean, this is just like an exercise, so yeah. And yeah, if you see these perfect and difference of squares is always useful, like especially when you see like just something to an even power, like I don't know, a to the 8th, and then you minus like I don't know 4, some perfect square. Then you use this. If you see some polynomial with these terms that look suspicious, then you use like square root binomial instead. Sometimes you'll have to like make use of both, but those are more complicated ones, so yeah, we won't be doing those. And yeah, I see people already sending me answers. Yeah, just quickly do these, and yeah, we'll get more practice with this later on in class. All right, so I think most people have done it. And yeah, the answers are 2x plus 3 whole squared, and then 2x minus 9 times 2x plus 9. All right, so yeah, it's just looking to see, oh, like we can kind of like match up when it's like the square of a binomial. We can kind of like see, well, first of all, you factor out all the constants. Like if there's like if it was like 8x squared plus 24x plus 18, we can factor out a 2. First get rid of that. All right, and then we can like, and we shouldn't have any like square roots or weird things left over from non-square constant factors. So then we notice that if it's going to be a square, then this will force the linear term to be 2x, right? Because the quadratic term is j squared x squared. Then we see this constant term, makes this a 3. And then all we have to do is check the linear term, and we see that lines up with everything. And that makes it the square of 2x plus 3. For 4x squared minus 81, we see that 4x squared is 2x entirely squared. 81 is equal to 9 squared, and that just directly gives this. So yeah, I hope that was easy enough to do and understand. So yeah, we'll see more of factoring things that don't have squares in them in the next couple of slides, and more complex applications of this. So now is factoring by grouping. Most of the time, well, it says as a last resort here, but a lot of quadratics, you can't immediately factor like an x out of it. You can't turn it into a difference of squares or the square of a binomial. You need to guess and check to see if it can be factored. And for the first concept here is factoring by grouping. It's simple. It's just that a times parentheses c plus d is equal to plus b times parentheses c plus d is equal to a plus b times c plus d. And yeah, here we've already grouped it for you if you look and think about it carefully. But yeah, just use like this concept to factor this quadratic, and when you're done, you can send me or one of the TAs. Don't forget your answer, your factorization. So I've gotten a couple of answers for this, so I'll just quickly go over it. This quadratic is also 6x squared minus 11x plus 4 if you want to check your answer later. But to factor it, you see that 6x squared groups with negative 8x, and then negative 3x plus 4 form a group. So then you in 6x squared minus 8x, you factor out the common term of 2x, so it's 2x times 3x minus 4. Then it's minus 3x plus 4, which is just minus parentheses 3x minus 4. The factorization is just 2x minus 1 times 3x minus 4. Be careful, do not make sign errors, do not accidentally swap the 4 and the 1 or something. It's 2x minus 1 times 3x minus 4. And so yeah, that's how you do this. As a quick check, you can just expand this. 6x squared, you can see quickly from the quadratic term, negative 3x, negative 8x is negative 11x combined plus 4. So yeah, it works. And then you see. And so yeah, that's how, if you want to change it so you can group the terms like this, you can, but most of the time the terms are not grouped nicely like this for you, as you'll see. So then you'll just have to you might want to try and create terms to group, or you might want to guess and check, as we'll see as well. So yeah, note in that the previous example, negative 11x is already split up. We'll need to do that ourselves for complicated quadratics though, and we need to guess and check. The key is to find a pair of numbers whose product is AC and whose sum is B. Then we can rewrite the polynomial group, and what they mean is if you want 6x squared minus 11x, this should be plus, sorry, it's not consistent with the last one, plus 4, and you want to factor this, then you have to think two numbers, how do we split this negative 11x into two numbers whose product is equal to 6 times 4, and that would be negative 3x, negative 8x. Negative 3 times negative 8 is 6 times 4. Perfect. So we want to do that with this. Or you can or there are other ways to do it too, to think about it too, but yeah. This is what is intended, is to factor it in that way, two numbers, they sum to negative 23, and the product is 6 times negative 18, which is negative 108, I believe. So yeah. Your goal is to find those two numbers and then split it into some of those two terms so you can group. So yeah, just go ahead and attempt this, and yeah, try to do it using grouping and not anything else for the time being. But I'll go over multiple ways to think about it as well. Yeah. Alright, so I'll go over this now. To see what two numbers sum to negative 23 multiply to negative 108. Well, what are 108's factors? You can quickly run through them in your head, right? There's 1, 2, 3, 6, 9, and then there's 1, 2, 3, 6, 9, 12, 18, 27. And yeah, if you just stop and think, then you'll see that negative 4, I mean, no, not negative 4, negative 27, positive 4 are the terms you want to split this negative 23x into to group. So it's 6x squared minus 27x plus 4x minus 18. And then you can just group this with this. So that would be 2x times 3x plus 2 minus 9 times 3x plus 2, giving you your factorization 2x minus 9 times 3x plus 2. Don't be daunted by the fact that it's negative 108, and just think about the factors. Also, take advantage of the fact that this is negative 23, so you can't have anything like 9 and 12 to split into, since like that would have a common factor of 3. 23 is clearly not divisible by 3. So yeah, only try things that you can't immediately eliminate. You can also think about this just straight up factoring, as some people did. If you've gotten used to it, you can do it pretty quickly, run through possibilities. 6x squared. Well, how can you factor 6x squared into a product of like two integer purely linear terms? Well, there's 6x times x, or 2x times 3x. So first, I don't know. You can try. Well, we know 2x and 3x works. So we're just gonna cheat a bit and try that here. We also know the constant term is gonna be negative. So one of the constants here is one of them has a minus sign, one of them has a plus sign. We don't really know which one it is yet, but like, remember, if we flip it, then it'll reverse the linear term, and that'll tell us that all we need to do is flip the sign. So if we get a sign flipped once, it won't be that hard to notice and change to the right one. All right, so in this case, we want a number, like a big number. So these two multiply to 18. We know we want a big number that'll make this like negative 20 something, and a smaller number that'll offset that a bit to get to negative 23. If we want the factors of 18, 6 isn't big enough. And then 9, and then this will be 2. Yeah, and 18 is too big to go here if you try it. And yeah, this is just how you try factoring. If you like try 6x times x minus something, you'll see that it doesn't really work out. Like, I don't know, you can try, so you want a minus sign here maybe, and then what would you try? Minus 6 plus 3? No, that's gonna be negative 33x. That's not gonna work. Yeah, you can just run through all the possibilities in factoring, and know, of course, like, actually, I wrote like 6x plus 3 times x minus 6, right? Well, you actually know not to try this, because 6x plus 3, you can factor 3 out of that. And clearly you can't factor 3 out of this negative 23x here, so that's not going to cut it. So you can just eliminate these factorizations, limit it so that like the number, first of all, you factor all the original constants out of that, then you get the polynomial who some three numbers don't share GCD, and then you factor it, but make sure the constants and the linear term coefficients are relatively prime, as just to further eliminate more like multiplication checking that you have to do. All right, so yeah, that's just how to factor this. It's 2x minus 9 times 3x plus 2 again. And yeah, that's just how to think about it. The key is just like the linear terms product that you get from like the linear terms product you get from the constant times linear terms summed up is equal to the final linear term, and then of course the constants multiply to the final constant. So yeah, sum to the linear term multiply to the constant. That's how you think about like this factoring. And of course, the coefficients of the linear terms you factor into, it comes from the factors of the quadratic terms coefficient. And so factoring quadratics, these two in-class problems, these two are a bit different. So, and I'll give you a little while for these. Our first problem is to factor 256x to the 8th minus 1 completely. I will tell you there are going to be, I believe, 4 terms you can factor this into. Not all of them are going to be linear, but yeah, you can factor this in. You should get 4 terms as in your final answer, is what it means by completely. And number 2 is like starting to get into like variable problems that turn into quadratics, solving quadratics. So yeah, just use variables to find to set up and find equations for the radii, and then you'll get quadratic, and then you'll be able to solve it. And so yeah, I'll give you a little while for these. And yeah, once you're done, you can send me or one of the TAs your answer. For this problem, I just assumed that, like, the center of this circle lies on the diameter, even though it doesn't quite say it. All right. Just to not, because otherwise you can't exactly solve it, and that'll just make it more annoying, complicated. So you just take this small circle center to be on this diameter AB. I'll give everybody maybe 3 more minutes. All right, so this first one, first of all, 256x to the 8th is definitely square. It's 16x to the 4th squared. So that gives us the factorization, first factorization anyways. 16x to the 4th minus 1, 16x to the 4th plus 1. Oh, but then we notice 16x to the 4th is also square itself. You can further factor it. Or actually, to like save a bit of space, I'll solve these. So we have 16x to the 4th plus 1 still. You can kind of factor this more, but like into real numbers, but we won't go over that. We'll just stick with difference of squares for now. Times, then we have 4x squared plus 1, 4x squared minus 1. And finally, we notice that 4x squared minus 1 is still difference of squares. So that finally gives us 16x to the 4th plus 1 times 4x squared plus 1 times 2x plus 1 times 2x minus 1 as our final result for number 1. It has 4 terms. These are the 4 terms. And yeah, that's how you do this. You break it down step by step. And eventually, if you get used to it enough, you can like instantly just like string this out into like all these like plus ones and then this final minus 1 at the end. But yeah, that's how you just break it down step by step. Remember, if there are still difference of squares, you can factor them out. Don't leave them unfactored. A lot of people just stopped at this step. Well, quite a few. But yeah, just factor it completely into smallest terms as possible that still have integer coefficients. Alright, yeah, that's basically this. For number 2, two circles are internally tangent A, diameter AB intersects a smaller circle at C. A shaded area, meaning this gray stuff in between, has area 9 centimeters squared, 9 pi anyways. BC is 4. What's the sum of the radii of the two circles? Alright, so like Does anybody want to go over? Does anybody want to show this problem? Or yeah, Vincent is volunteering. So first, what do we set our variables to be?
Our variable is x, and that shall be the diameter of the smaller circle. So the radius of the larger circle is 4 plus x over 2. And the area of the circle, the larger circle, will then be 4 plus x over 2, the whole thing squared, times pi. The smaller circle will have area x over 2, all squared, times pi. The first one is the same as x squared plus 8x plus 16 over 4 times pi. The second one is the same as x squared over 4 times pi. The larger one subtracted by the smaller one will be 2x plus 4 times pi, which is equal to 9 pi. So x equals 5 over 2. So the radius of the smaller circle is 5 over 4, and the radius of the larger circle is 3 and a fourth. Adding these up, we get 4 and a half.
Yeah, that's right. I'd say that these are not the most convenient variable choices, but yeah, it certainly works out. Then you get this is 5 half. The other one's diameter is one of the other one's diameter would then be, I believe, wait. And yeah, anyways, this one would be 5/4 radius, and then the other one should be, I think, 2 more than that. So that would be 13/4 in radius. All right, so then, yeah, I would actually pick the radii to be the variables, because then you don't have these fractions sitting around. Then just to see what that would look like, then you see the diameter's difference is 4. The radii is different, so then be 2. So then you have pi times r plus 2 squared if you make r the small ones, times r, pi r squared is equal to 9 pi. From that, you immediately get 4r plus 4 is equal to 9. And then it follows the answer of the problem, that's sum of the two radii. So yeah, that's just how you do this. Note that in this case, the quadratic term actually canceled out nicely. So there wasn't any like real quadratic technique being used here. Yeah, but in some problems it won't. Some problems you'll have to solve factor quadratics. And yeah, the answer might not always be an integer, as we'll see. As we'll soon see. And we might have to finish this off early. But yeah, I'll go over more on quadratics later if that is the case. So solving a quadratic and factoring. When you solve a quadratic like ax squared plus bx plus c, you are finding the value of x such as the expression equals 0. These solutions are also called roots or zeros because like if you two numbers multiply to 0, if a b equals 0, a is 0 or b is 0, at least one of them. By the same reasoning, you have a quadratic factor like this. Then you know that when it's equal to 0, at least one of these must be 0. So either x is negative b over a, or x is negative d over c. You can see that these values when plugged in will make each of these zeros, and just like they said here. So in that case, solve this equation. First, move the terms all to the same side, and then factor, and then solve it based off your factorization. And see which two values of x. Quadratics always have two solutions, although if it's a perfect square, there will only be one distinct solution. Anyways, find which two solutions there are to this. We use what we talked about earlier to get the factorization. Yeah. Yeah, privately send me your answer once, or send the TAs your answer once you're done. Alright, you see most people getting this right, so I'll just go over it. So first off, to factor 6x squared minus 7x minus 3, try things and you'll see maybe like 3x minus and then 2x plus something is equal to 0. You'll see maybe like we try what can 3 factor into? Can only factor into so many things. What? 1x, 3. This gives 6x squared plus 7x plus 3. So we'll just reverse the signs. That should give us our desired answer. 3x minus 1, plus 1, 2x minus 3. We can expand this, see that we get our answer, so that our desired quadratic back. So we solve, we get x is equal to what? 3 halves, negative 1/3. Those are our two solutions. So yeah, these solutions just follow immediately from factoring. There isn't really much thought into that. Just like just set this equal to 0. No, whoops. Just set this is equal to 0 and solve for it. Set this equal to 0, solve for the x. And yeah, so the hard step in here is really just the factoring part. Just understanding that like that's where the two solutions come from is all you need to get the solutions. And so I believe that this is all we'll do. This is where we'll stop for today. Next class we will discuss how to deal with quadratics in general, ones that don't factor into integers. Like, I'll get rid of this now. Quadratics that don't factor into integers, like x squared minus 2x minus 1. How do you do this? And we'll discuss that tomorrow. How to deal with general quadratics. And yeah. Anyways, that's the end of today's lesson. I'd originally probably assigned some like homework problems that included stuff we haven't discussed yet, but I will adjust that as necessary. And so yeah, class is over now and you can leave. And this meeting, I started recording a bit late, but yeah, it'll be posted.
Thanks. Bye.
Tasty farm. All right. So you had trouble factoring?